Today we're going to be doing division of complex numbers, but before that we need to learn what the conjugate of a complex number is so that we're able to do this. Just say we have a complex number z equals a plus bi. The real part would be a, the imaginary part would be b. The conjugate, the symbol we use for that is z with a bar on top. So z bar would be a plus bi. So all we do there to change a complex number to its conjugate is to change the sign of the imaginary part. So let's look at what actually happens when we have a complex number and its conjugate. It's got some interesting relationships. First line here afterwards says the sum of a complex number and its conjugate, so z plus z conjugate, would be a plus bi, that's z, and then plus a minus bi, which would be 2a, which is a real number. That's really interesting. Sum of a number and its conjugate has got to be a real number, because as we said, we changed the sign of that imaginary part, so it knocks it out. Then we've got the product of a complex number and its conjugate. So z times z bar, I'm going to do an extra line of working out here. So when we expand this out, we're going to get a squared minus abi plus abi minus b squared I squared. But remember, I squared is equal to -1. We also have these two middle terms which have knocked each other out, because this is very much like a difference of perfect squares kind of situation. So that means it's going to be a squared plus b squared. And this is also a real number, it says in this final line. Because remember, we've got -b squared times -1, so that becomes plus b squared. Okay, this does not constitute a formal mathematical proof, but we're going to explore just some characteristics of conjugates here. You'd of course be able to do a proof of this if you just used, generic values of z would be a plus bi z1, maybe add z2 of c plus di, and you'd be able to prove these things. But I'm going to leave that as an exercise for you to do. So we've got two values of z here. We've got z1, our first complex number. We often use z to represent it, is 2 plus 3i, and our second complex number is z equals -4 minus 5i. So to do part A, what this is telling us is that we're going to find the conjugate of z1 and we're going to add that to the conjugate of z2. Conjugate of z1 is 2 plus 3i, so the conjugate is going to be 2 minus 3i, and we're going to add that to the conjugate of z2. Real part still stays as -4, so -4, and the imaginary part changes sign, so plus 5i. Always like to write it real then imaginary, so we've got, let's compare that with doing the sum first and then doing the conjugate. So if we do the sum first, we're going to have 2 plus 3i plus -4 minus 5i. And we're going to take the conjugate of that after we clean it up. So looking at that, that's going to be -2 minus 2i, and we're taking the conjugate, so we just put a line over the entire thing. And taking the conjugate of that, -2 stays the same because that's the real part, but the imaginary part changes. So it appears from this quick example that we've done here, again, not a formal mathematical proof, but you're welcome to explore that. It appears that the order that we take the conjugate doesn't matter. So we can take the conjugates and then do the sum, or we can do the sum and then take the conjugate. So this one, z1, z2, we're taking the conjugates first and then we're doing the product. So we need our values of conjugate of z1 and z2. So it's going to be 2 minus 3i, and then in brackets -4 plus 5i. Okay, let's expand this out. Okay, let's now see what happens if we did that multiplication and then took the conjugate. So we're going to do z1, z2, the product first, and then the conjugate. Okay, so we need to take the conjugate. It was remiss of me to not include that earlier. So we'll just pop it in. And when we take the conjugate of that, we get 7 plus 22i, as we'd hoped. So this relationship is pretty interesting because it tells us that the conjugate of a sum is equal to the sum of the conjugates. And it also tells us that the conjugate of a product is equal to the product of the conjugates. Now, one more thing while we're still in conjugate land is I wanted to mention the modulus of a complex number. It says the modulus of a complex number, we're representing that with the regular modulus symbol. That also applies to complex numbers. And that's given by this equation here. Now, you may have noticed before, when we did z times its conjugate, we actually ended up with a squared plus b squared. So, because the modulus of z is the root of a squared plus b squared, we're just saying that must be equal to the modulus squared. We're going to be revisiting this modulus. It's really going to be important when we're graphing our complex numbers. Okay, why did we talk about conjugates? 1, I think they're pretty interesting, but 2, they actually have an application within complex numbers. I really like thinking of this in terms of stuff that we've done before. There's a really clear similarity between the process of expressing a complex number with a real denominator and the process for rationalizing the denominator of a surd expression. Just to be very clear, we cannot have an imaginary denominator. So let's be even clearer, we must have a real denominator. It is improper to leave something with an imaginary or a complex denominator. It needs to be real. Now remember when we did rationalizing denominators, if we had something like this, 3 plus root 2 on root 3 minus root 2, what we actually did to get rid of that is we multiplied by root 3 plus root 2 on the denominator and numerator of a fraction. So what was the critical thing there is we changed the sign of the term in between the surds at the bottom here. Really important. So we're doing a very similar process when we're dividing with complex numbers. What we're going to do is we're going to look at our denominator and we're going to multiply by the numerator and denominator will be the conjugate of that. So 3 plus 4i, 3 plus 4i. So let's continue this. So what are we going to have? On the top, we must put brackets around things. 5 plus 2i, 3 plus 4i. And then on the bottom, 3 minus 4i, and we multiplied that. Same thing, we multiplied the top by, the conjugate of that denominator. Now let's go ahead and expand everything. Got to be really careful when you're doing these complex number examples that you keep an eye out for when you've got, get it? Keep an eye out for when you've got those I squared terms. Because remember, I squared is equal to -1. Okay, we've nearly finished up here. So that's going to be 7 plus 26i on 25. Now, for some reason, in the complex number world, we do not like to leave our answer looking like this. It's just one of those strange conventions. What the examiners in Year 12 would prefer you to do is write 1 on 25 here, and then put your 7 plus 26i. I don't know why they prefer it, but they really do. And it's perfectly fine to leave that with that factor out the front. You don't need to distribute that and get 7 on 25 plus 26 on 25i. Really, really important that we leave it looking like this lovely final form here, because that's what they expect of you in Year 12. Okay, let's have a look at another example. Now, there's multiple ways you could do this, but if we follow the same process that we did before, you'll see that it actually works out pretty nicely. On the bottom, we just have 2i. That's like we've got a real part of 0 plus 2i. So the conjugate of this would be 0 minus 2i. So what we're going to do is we're just going to multiply the top and bottom by negative 2i, negative 2i. Now, eagle-eyed people out there might recognize that we could have just multiplied the top and bottom by I, or by 2i, because that would eventuate in getting an I squared at the bottom. Sure, that works, and if you're comfortable with doing that, go for it. But I know some people like to just remember one rule for everything, and multiplying by the conjugate will always work. So that means, on the top, we're multiplying everything by that negative 2i, and on the bottom, we're going to have minus 4i squared. This is where the power of doing a negative will come in there, because if we just zoom in on the denominator for a moment, I squared is negative 1, so that means our denominator will be positive 4. It's really nice that we multiply by negative 2i over negative 2i, because it means when we do the denominator, we're going to end up with a positive, and we don't need to worry about dealing with a negative later. On top, what do we have? Keeping in mind, I squared is negative 1. So that means we're going to have 10 times negative 1, so negative 10 minus 6i on 4. You do need to be careful though, because we can take out a factor of 2 there, and perhaps we could have thought of that a bit earlier on. So let's take out that factor of 2. I'm just going to take out 2 and not negative 2 for the purposes of cancelling. So we're going to get negative 5 minus 3i. Actually, no, let's take out that negative, because then we wouldn't have to deal with that. So negative 2, and then 5 plus 3i. That looks much better. All on 4. So we're going to cancel off like that. And then remember how we like to leave our final answer? We don't want to leave that as negative 5 plus 3i in brackets all over 2. We would like to write that as negative a half 5 plus 3i. So the really, really critical thing here, you must not have an imaginary component in your denominator ever. So let's go ahead and look at the next example. So here's another example. We've got z1 equals 6 minus 3i, and z2 equals negative 5 minus 3i. We want to express z1 divided by z2 in the form of a plus bi. Okay, so z1 over z2. That's going to be 6 minus 3i over negative 5 minus 3i. In order to continue with this problem, we need to make sure we have a real denominator. So we're going to multiply by the conjugate of that denominator. And remember, we're allowed to do this because this conjugate divided by itself is equal to 1. So we haven't changed this. We can multiply equations by 1 till the cows come home, and it hasn't changed anything at all. Okay, so we're going to expand out that numerator. On the denominator, we're going to take advantage of the fact that we have a difference of perfect squares kind of situation. Okay, cleaning things up. Keep an eye out as always for those I squareds because they're equal to negative 1. So that would give us 1 on 34, negative 21 plus 33i. I do notice that it asks for it in the term of a plus bi, so I think in this particular circumstance we do need to expand that out, but normally that is not expected of you in an exam situation, unless they specify to the contrary. Now, we haven't done much of this on the calculator yet. Let's have a look at how that's done. So to check our answer here, there's a few things we need to do for our calculator. For the first time ever, you want to make sure you're in complex mode here, so turn it out of real mode. And we want things in terms of fractions, so make sure that that is in standard. If we look at our menu here, if we go to Math 2, that's where I actually lives. So if we wanted to write in our question here, your calculator, like a lot of things, will automatically write something with a real denominator. So if we just type that in, we've got on the bottom minus 5 and then minus 3i. If we set that to work, you'll see that it actually expresses it in the expanded form. But that's okay. You're able to interpret that. Also, be sure on your calculator you're not just using a random letter I. Make sure you're using that I in the Math 2 menu. Okay, I'd like you to have a look at the next one. There's actually two examples that I've got here. This one I'm just going to do without speaking, and you can ask me if you've got any questions. And this final one, I wanted to give you a break and you can just have a chance to copy that out. So if you want, you can pause the video now and copy out this solution, and then you can watch me have a look at this one. Okay, so remember, you cannot leave a denominator with an imaginary component. It must always be a real denominator. You've now got some questions to do, exercise 16b. Good luck and let me know if you've got any questions at all.